In this section, we'll be using this function as our model where the Q sub 0, or I would say Q naught, or the initial quantity, is proportional to its growth, and K is the constant of proportionality. You can actually derive this equation by doing some calculus. We're going to skip that for now, and we're just going to go straight to that model. And that model can be used to talk about the growth of bacteria, to half-life of plutonium, to money situations. Many different models use this function. So let's talk about how we can use that function. The first problem, we talk about bacteria that's growing. It's proportional to its size of growth. And in a laboratory, we have the number of cells in a culture doubles every 20 minutes. If the initial cell population is 100, then they want us to determine a function. So we're going to take this model, and really our job is to figure out that growth constant. So they're going to give us enough information to hopefully do that. Let's write down the information we do have. The initial amount is 100 cells, and we're going to say that at time 0. That's why it's initial. And then we have it doubles, so twice 100 is 200, and that's going to take 20 minutes. So from this information, we're going to solve for that growth constant K. So let's see. When Q of t is 200, the initial amount was 100, e to the k, and I'm going to put 20 in here because when t is 20, Q was 200. Now let's do the algebra to solve for this. So we're going to divide by 100. Okay, so now we have to solve for k. How do we do that? On an exponential function, we need to take the natural log of both sides because the natural log and the exponential function are inverse functions. So we have the natural log of 2, and if you remember, we can take this, move it down in front, then we have the natural log of e. And the natural log of e is always 1. So this natural log and e cancel each other out, if you will. So we have the natural log of 2 equals 20 times k. So our growth constant is the natural log of 2 divided by 20. Now you can punch that into a calculator, and it would be approximately 0.03466, I think. But it's asking us for, let's see, the function as time. So we have Q of t equals Q naught, that's the initial, equals e to the k, that's the natural log of 2 over 20 times t. So that's my function. Part B, using that function, how long will it take, so that's t, for a colony of 100 cells to increase to a population of 1 million. So we want 1 million equals 100 e to the natural log of 2 over 20 times t, and this time we're solving for t, for how long. So I'm going to divide by 100, then I'm going to take the natural log of both sides, and the natural log of e going to cancel each other out, so I have the natural log of 2 over 20 times t. So now I want to solve for t, so I'm going to multiply both sides by the reciprocal. So I have 20 times the natural log of 2 times the natural log of 10,000. Right? And then punching that into my calculator, and I'm going to be using a TI-84, but a lot of your calculators have some of the same keys. Would punch that in, and I would get 265.75 And this is in minutes because the initial said it doubled, I believe, in 20 minutes. But if I wanted hours, I would then divide this by 60, and I would get t to be 4.43 hours. So make sure you know what they're asking for in terms of minutes or hours. Let's see, part C says if the initial cell population were 1,000 instead of 100, how would this alter our model? Let's look at that. It says if the initial was 1,000, and that's t is 0, and it still doubled, so it would be 2,000 in 20 minutes. Would that change our model? So we'd have 2,000 equals 1,000 e to the k times 20. Take the natural log of both sides and divide by 20. And I think you can see that k is the same, so because it doubled in the same amount of time, it doesn't matter what you start out with, just that doubling factor. All right, this next situation talks about the population of Brazil. And again, we can use that same growth model. Sometimes when talking about population, they'll replace Q, and I don't know why this book chose Q. They'll make it P's. It really doesn't matter. It's just some variable. All right, so let's see. The population at 1990 was 150 million. So it means our initial population was 150 million. And T of 0 is going to correspond to 1990. So that's our initial population. Assume that the population continues to grow at a rate of approximately 1.2% a year. That is our growth constant. That is K. But we need to change that percent to a decimal, so we move the decimal to the left 2 places. All right, so we know K. Find the function in millions. Let's see, I think we have Q of T equals the initial population, E to the kt. That's the function that we're looking for. Now we're going to use that function to answer this question. It says if Brazil's population continues to grow at that same rate, find how long it would take for the population to double in size. All right, so if we started out, if the initial population was 150 million, then double that would be 300 million. So we want to say, all right, so when Q is 300, what is T? So one more time, we're going to take the natural log of both sides. And keep in mind, those cancel each other out, so you just have that exponent. And then we need to solve for T. And then once again, go to the calculator and type that in. And so you would get T to be approximately 57.76 years. So it would take that long to double Brazil's population. This next part, part B, I thought was worded strangely, but I took it straight from the book, straight from the computer. It says, using the time found in part A, what would be Brazil's population if the growth rate were reduced to 0.8% a year? Right, so remember it took us 57.76 years to double if that was using that rate. So we're going to have to change our model to be our initial population still 150, but our growth rate is 0.8% a year. So we need to move that decimal again to the left 2 decimal places. And they're asking us to now take 57.76 years and plug it in for T and calculate the population. It should be less than 300 million because that's how long it took to double. So we're going to have Q of 57.76 years. I think that's a 7. All right, so again, we want to be very careful about pushing that into our calculator. and I get 238.11 million. Now that's a reasonable answer because if we had a higher growth rate, we would have been at 300 million, so we should have expected a smaller answer. All right, here is another situation using that same model. It says that the temperature is constant, the atmospheric pressure, this one's measured in millibars, varies with the altitude above sea level, H, in accordance with this model. So notice they've used P's instead of Q's. They've used H instead of T. All right, so let's look at the information. The atmospheric pressure is 1,113 millibars at sea level. Sea level would mean there would be no height. So that's our initial pressure. So that's going to be P naught. Then the next one says the pressure is 90 millibars when H is 20. And they want us to find the pressure when the height is 50. So again, we're going to come back up here and get our model basically to solve for K. And then once we solve for K, we can answer that question. So let's see, 90 equals our initial quantity, E, notice there's a negative K times 20. Now where am I getting these numbers? 20 and 90 match up. When H is 20, P is 90, and then we have this initial amount that was given here. So what we need to do is solve for K. So I'm going to divide both sides by 1,013. And I'm going to take the natural log of both sides. And when I do that, the natural log and E cancel out, so I'm just left with the exponent. And then when I solve for K, I'm going to have the natural log of 90 over 1,013 divided by negative 20. And punching that into the calculator, I get approximately 0.12104. So my model should be P of H, and I need to put that negative back in there because it's part of the model, 0.12104H. So now, no matter what H is, I can find the atmospheric pressure. But they ask us for what that pressure when H is 50. So I'm going to plug in 50 for H. I'm going to reach for my calculator, type all that in, so you can tell the pressure goes down quite a bit as you go up in altitude. Now it asks us how fast is the atmospheric pressure changing with respect to altitude. Whenever you see that, how is it changing, that means you need to take the derivative. All right, so if we have, remember our model, we need to take the derivative of that. So we leave that constant alone. This gives us some practice on how to take the derivative of our exponential function. Remember, we leave it just like it is. But then we have to multiply by the derivative of that exponent, and H is our variable. So I need to have a negative 0.12104. And then, of course, you can multiply those two numbers together. Depends on how many decimal places you want to round to. Right, so that's my derivative in general, and they want to know how fast is it changing when the altitude is 20 kilometers, meaning they want to know when H is 20, and they want to round our decimal to 5 places. So I want to evaluate the derivative when H is 20. Again, you would need a scientific calculator, punching that in carefully, and I get negative 10.894, and this is going to be millibars per kilometer, which means it decreases, the pressure decreases as I go up in kilometers, which is certainly what we saw as we looked at the pressure at 0, at 20, and at 50 kilometers. Let's talk about the half-life of a radioactive substance. And what does that mean, half-life? In general, let's say we started out with 100 grams of plutonium, it would take this many years to get down to 50 grams. so it lingers a long time. So in this example, it says 10 grams of plutonium is released. How much of it will still be present after 55,000 years? Well, the amount, and I'm going to use P for plutonium, so I'm going to use this model. And again, you could go back to Q if you would like to. So our initial amount is 10 grams, and we're going to always let that time be 0. And then this is the sentence that's kind of lurking, half-life. Well, that means 5 grams would be present in 24,360 years. So we use this information in order to find K. So again, we've got this matching up with that number. When T is those many years, that's the amount that we have. So we divide by 10, take the natural log of both sides, and then divide by that number. And that would be our value of K. Again, if you wanted a decimal approximation, I got K to be negative 2.845 times 10 to the negative 5th. All right, so my model would be P of T equals P naught, which is 10, e to the K times T power. Right, and I believe the question asked how much of the plutonium will still be present after 55,000 years. So that's T. So I want to evaluate this at 55,000. Now if it took 24,000 plus years to get down to 5 grams, we should have a lot less in 55,000 years. So carefully punching all of that into the calculator. In 55,000 years, we still have 2 grams of that plutonium. If the amount of plutonium in a certain area is found to be 6 times the safe level, find how much time must elapse before the safe level is reached. What are we looking at here? Whatever that initial amount is at time 0, we want 1/6 of that because it was 6 times the safe level. So if it's 6 times the safe level, I want to divide by 6 to get back to the safe level. So about 1/6 of the initial, that safe level. How much time is that going to affect? Now remember, this is still plutonium. It still has the same half-life, so we already know that the growth constant is exactly what we solved for before. Okay? So our model, remember, is, I think I used P, is our initial amount, so I'll change this back to P's, or Q's, whatever you would like. So how can we put that in? If we don't know what we started out with, we can't assume 10 grams. Well, we can just make a ratio saying, all right, I want 1/6 of my initial amount. Can I solve for T? You might be thinking, well, you have too many variables, but let's look at this. If I divide by this initial amount, whatever that is, it's going to cancel it out. So we're just looking at a ratio. I want 1/6 of that. Okay, so again, we're going to take the natural log of both sides. And this is going to allow us to solve for T, divide by this. And I will get 62,979 years. I'm pretty sure I rounded to the nearest year. So if you've got 6 times the safe amount, it's going to take a long time before you get down to that safe amount. The last example we're going to look at is carbon dating. Hopefully you've heard about carbon dating. It tells you how old something is. And so this piece of wood is found to contain 30% of C14, which is carbon-14, that it originally had. When did the tree die from which the wood came? Now I agree this is a very poorly worded question, but I got it straight from the book. What they need to tell you is that the half-life of C14 is 5,730 years. We don't know what the initial amount is. but we have that half-life. So Q naught is the initial amount at time 0, and twice that, nope, not twice that, because it's not a double life, it's the half-life at 5,730 years. And again, we're going to use this to find K. And just like in the last example, we don't know what that initial amount is, but we saw the algebra that that's going to cancel each other out. So we want half the initial amount in 5,730 years. So we just get that ratio, dividing by 5,730, and I get K to be negative 1.2097 times 10 to the negative 4th power. So my model is that for carbon-14. Okay, so now we know what K is. It says a piece of wood is found to contain 30%. Well, 30% of what it initially had would be 0.30, 30% 0.30 times that initial amount. So we're going to say 0.30 of the initial amount equals the initial amount. So I'm going to use my model here, and I want to solve for t. So again, dividing both sides, that's going to cancel, taking the natural log of both sides. Keep in mind that natural log and e undo one another, and now I'm going to divide both sides by that quantity. And when I punch that very carefully into my calculator, I get t to be 9,953 years. I've rounded to the nearest year. So keep in mind, here is our model. The basic part of the problem is they are going to tell you the initial amount, or they're going to tell you enough to not need to know the initial amount. Then they're either going to give you a half-life or some other quantity so you can solve for K. Once you solve for K, you have your model, and you should be able to plug in numbers as much as you need.